So are there any questions, doubts you can ask?
Sir,
Anybody? Yeah.
sir, sir, I am still not clear. In isotropic, we are taking the F is function of sigma and work potential WP.
Yeah, plastic work of stresses and
Uh,
alpha,
uh, uh, not
bike stress.
sir, in isotropic we are not considering alpha.
No, that
We
you are,
are
yeah, yeah, in the isotropic hardening you were saying, yeah.
yeah, and in kinematic we are considering just sigma and alpha. Why not we are considering WP and alpha both in kinematic, or it is
No,
by
the
definition?
WP comes with the isotropic hardening. No, the kinematic hardening is then dependent on alpha, that is bike stress.
This is by definition, sir.
Yeah,
That
yeah.
okay.
Anybody, any other question, doubt?
Hello.
Yeah.
Sir, what is the next to this
Be little louder. Your voice is very low.
sir, how is the backstress represented in the graph? That is,
How is?
backstress. Backstress is
Yeah.
represented in the graph.
So I had in the I had told you, no, that different. If you look at the stress strain graph, I had told. So when you go into the tension and then in the compression zone, so the yielding in compression is taking place at a lower stress than what it has started in tensile loading. So that means in tension there is a higher yield stress and in compression it is lower. So you can say that the origin of field surface has shifted towards tensile side. So that is how it is reflected. No, if you recall, I had drawn the graph. No, that stress strain graph for the kinematic hardening. Do you
So,
remember
sir,
that?
yes, sir. Whenever yield surface is translated, so that
Yeah,
translation is basically the backstress.
yeah. That amount of translation is back stress.
Okay, and that translation is in that compression zone or the tension zone whenever we
No,
are
it
using.
is no, when you are going from tension to compression. So now when you go from tension to compression, so the yield surface is translating towards tensile side, so the compressive yield stress is lower. And when you go from compression to tension, then also there would be translation of the yield surface towards the compression, and there would be lower yield stress in tension. No, in the cyclic manner, if you go to tension, compression, then compression to tension again. So it will keep translating along the tensile side or the compressive side, depending on which direction you are loading it.
Okay, sir.
So alpha can be positive, it can be negative. Positive means positive alpha means initial loading is in tension, and then in compression you will have lower yield stress. And negative means initial loading is in compression, and then you are going to tension. So compared to compression, tension yield stress would be lower in that when alpha is negative.
Okay, sir.
Yeah.
Kinematic hardening, like what we will say, like yield stress is a function of what?
Yield stress, no, we are not saying actually yield stress there. So if you look at in the yield function, we are keeping that term as constant sigma y naught, but origin of the yield surface is changing. So effectively, the state of stress at which yielding will take place is different in tension and compression. So yield stress, if you remember, we said in kinematic hardening that it is sigma y naught, but there is a alpha term. So we have sigma xx minus alpha xx and those kind of terms.
Okay, so basically alpha does the thing,
Yeah,
which
alpha is the term which takes care of this kinematic hardening.
okay, sir. Sir, and while deriving the Prager's constant, that is 2h by 3,
Yeah,
uh, you divided by a term that is sigma xx minus 3 by 2 alpha xx.
yeah.
Can't it be 0?
So, it is a common factor, so that is what we said. And yeah, the question is whether minus 3 by 2 alpha xx can be. I think it can, no, it won't be 0. If it is 0, that means then your yield surface is reducing to a point, so that will not happen. So it won't be 0. Yeah, it won't be 0.
Okay, sir. How did you come that? How we come to know, sir, that yield surface reduces to a point?
No, because now if you have sigma xx minus 3 by 2 alpha xx 0, so then you are saying no, the yield function, that term is going to be 0, now the square root term which is there inside. If you see, I think, let me open that. So see here, if you look at this, this f, what you see over here, this one, I
Not
think
able.
Achha, okay, I have not shared it, so let me unshare that file and share this here. So if you see now, is my screen visible now?
Sir, now I
This
can
one.
see it.
Yes.
So if you look at this expression, so if you look at this term, so this you can write it as sigma xx minus 3 by 2 alpha xx whole square. So if that term is 0, then you are saying that basically this term is 0. And that means the yield surface is, then you are saying is essentially reducing to a point. That will not be possible. That will not happen. When the material is yielding, of course, when you start with zero load, then you have f equal to minus sigma y naught. But when the material is yielding, sigma xx minus 3 by 2 alpha xx cannot be 0.
Okay, so sir, here yield surface is a point, right? Um,
No,
in
it
this
is not a
case,
point. It is a surface.
sir, in this uniaxial case.
Uniaxial case, it will be, yeah, uniaxial case, yeah, we have only, so it will be, yeah, it will be a, not a point, but it would be actually line segment, you can say. It will be a line segment.
Okay, and the end points of the line segments are my yielding points, like that.
Yeah.
So that line segment will reduce to 1 point.
Yeah, if we have this sigma xx minus 3 by 2 alpha xx 0, then it will reduce to a point, single point, which is not possible when the material is actually yielding. I mean that, yeah, that's okay.
Okay.
Hello, sir.
Yeah. Yes, tell me please.
We are using, sir, we are using Newton-Raphson method for that B transpose sigma.
Yeah.
So as sigma is non-linear here, so
Yes, nonlinear function of strain,
yeah,
yes.
so in Newton-Raphson we assume some value for x. So
Yeah.
which value we have to assume here?
So see, we will start initially with the whatever load is there. We will divide that into a number of steps. So initially we will start with the initial guess of the displacement vector. Would degrees of freedom would be actually starting with a zero null vector, and then the subsequently, once a particular the solution converges for one load step, and then when we go for the next load step, so we will take the initial solution as the converse solution of the previous step, and that is how we will proceed. So initially when we just start, we take the displacement vector as a null vector, and then subsequently we take the converse solution of previous step as the starting guess for the next load step.
Okay, thank you.
Yeah.
Sir, if you
So
will take,
tolerance also we have to define, no?
Pardon?
Like tolerance also we have to define, no?
Yeah, we have to define the convergence criteria. Yeah, so you can put the convergence criteria either on stresses or on the displacement, that the stresses between from the two consecutive iterations, the difference in the stresses should be less than certain tolerance.
So normally the softwares and all, when we give input, like I used to do nonlinear in software, so their force tolerance as well as displacement tolerance comes into picture. Whether
Yeah.
both or also option will be there. So
You can either have the tolerance on the force vector, the net force vector, or you can have tolerance on the displacement vector. You can also have the tolerance on stresses. So yeah, that, but most common
that
ones
will
are
be
of
like
course
our,
the displacement and the force.
so that will be like our input only, something like displacement tolerance and all 0.5.
That is an input. Yes.
Okay, sir.
Yeah.
Thank you.
Sir, in lecture 17,
Yeah.
yes, sir. In lecture 17, when we are defining this del F by del WP, when
Yeah.
F is the yield function, and initially we have defined yield function is equal to sigma equivalent minus
Yeah.
sigma
I
y.
think somewhere it is there. So let me go there. Yeah.
Sir, in
So
lecture 17, first.
yeah,
Initial.
17. I am in the 17 only. Now the screen I am sharing is
Yes, sir. Yes.
lecture 17. So you are talking about now this one, right?
Yes, sir. Yes, sir. Sir, before that, we have
Hmm.
defined F equal to sigma equivalent minus sigma y, which is a function of plastic work.
Yeah.
So then we have defined this d of epsilon equivalent p divided by d of wp is equal to 1 by sigma equivalent, and
Yeah.
then sigma equivalent is equal to sigma y. But sir, initially we have taken sigma equivalent minus sigma y, so that must be 0, right? Means
Yeah.
this
So that
sigma
is what
y.
I said. This we are talking when the material is undergoing elastoplastic deformation. So there is a yielding taking place. So EF is 0. And if EF is 0, then we are saying sigma equivalent is equal to sigma y.
Okay, so sir, we are calculating this in order to calculate this del f by del wp, but f is
Yeah.
equal to 0 initially.
Yeah.
Okay, sir.
Sir,
Sir,
F
how
is
will
0 from yielding point to up to the point we are giving the load.
Yeah, we once the onset of yielding starts, and then if the loading continues, so F will always be 0 at every loading step. When we are increasing the load, there is a subsequent elastoplastic deformation, so F will be 0.
Okay.
Yeah.
sir, how will we find alpha?
How do we find alpha?
Yes, sir.
So we had discussed that, no, that we're using that one of the simplest model to find out alpha is that Prager's rule. So we calculate the incremental plastic strength, and then calculate like d of alpha xx is c times d of epsilon xxp, and that kind of relations. So we calculate the incremental plastic strength, and then we calculate the incremental back stress alpha, and then add to the previous value and get the total alpha.
Okay, that also we need to do iteration wise, right?
Yes. So that will also be part of iteration.
Okay.
That will be part of iteration. I mean, you won't do separate iterations for that, but it would be part of iteration. Yeah. Any other question? Anybody?
So
Okay.
finally, if we are everything we are calculating, that is, we have to substitute it in tangent stiffness matrix to
We have to
get the
substitute
initial
in.
confidence. Tangent stiffness matrix. That's CT.
Yeah. We have to substitute there. You need this expression for tangent constitutive matrix, which would be in terms of stresses. So you have to substitute that. You need plastic strain over there. So all those terms will be substituted there. So but no, you require all these once you solve that equation, you get the incremental displacement vector, then you have to do all these calculations to calculate the plastic strain, back stress, to calculate the stress itself, and all these calculations would be going within that iteration.
Okay, sir. Thank
Yeah.
you, sir.
Okay.
Hello, sir.
Yeah.
Sir, on this page, sir, little above.
Okay. Yes.
Sir, the value of CT should be C minus 1 upon A C. There should be C na before del F by del sigma.
Yeah. You are right. I think I just missed that. There is a C. Yeah. There has to be C. Yes. Here there should be CE. Yeah, correct. Thank you for pointing this out. I think others also please make a note of this, that there is a CE here. Yes. Any other question? Anybody?
Sir, suppose we have a non-associative flow rule.
Yeah.
Then that means that like suppose for associative flow rule or CT is symmetric. So like it is behaving in a similar manner as CE, that CE is symmetric like in isotropic material.
Yeah. No,
Even in any material,
CE is always symmetric,
any
whether
material in
the material is isotropic or anisotropic.
isotropic, yes sir.
Yeah.
And,
But because yeah, fine, then we will be having Q over here, and those would be different. So then it overall it will become unsymmetric.
so like why, like physically why is it so, sir? Like physically why it is becoming unsymmetric?
The reason is because the yield criteria and the flow rule, the how the plastic strains are involving, the two are different.
Okay, sir.
Because see, this term is coming, if you see, it is coming from the plastic strains. This second part in CT, what we have is coming from that plastic strain term, and yeah, so because of the basic differences coming from the plastic strains are evolving differently than the change in the yield function or the normal to the yield function, and the combination of these two makes the tangent constitutive matrix unsymmetric.
Okay.
Yeah, so any other question, anybody? So if there are no questions, let me start. Yeah. So now the last class I have discussed ultimately how to get CT for isotropic hardening and CT for kinematic hardening, and what are the associated calculations, how to get del F by del alpha and so on. Now the next question is coming, because if you know, ultimately the second part of CT involves actually stresses, plastic strain, all those quantities, because del F by del sigma is going to be in terms of stresses, and the yield stress, and which is a function of plastic strain or the plastic work. So we need those calculations. So today I'm going to discuss how to calculate stresses. So let me say that evaluation of stresses. So now the overall thing, what we are saying is that we have a tangent constitutive matrix, and let us say this is there for the I minus 1th iteration, and then we have incremental displacement vector. So this equation I am writing after assembly and imposition of boundary conditions, so the form will still be same. So we will have global tangent stiffness matrix in the previous iteration corresponding to the previous iteration into the incremental displacement for the current iteration is equal to right hand side, which is a combination of three terms, no, the body force, surface force, and also the contribution due to the stress in the previous iteration. So this entire load vector is corresponding to say previous iteration. So you have this as the final equation in after the application of Newton-Raphson assembly of the all the elements and then the imposition of boundary condition. And if you solve this, the solution of this equation is going to be, solution would be finally this delta di, that is what we would solve. Once we solve for the global this incremental displacement vector, then we can extract for each element the incremental elemental degrees of freedom vector, and from there that we can calculate the strain. So then you calculate the incremental strain epsilon. This will be now corresponding to ith iteration. So this will be equal to now this strain displacement matrix B times delta dE for the ith iteration. From this global vector you are going to extract the vector of elemental degrees of freedom, that is vector of incremental degrees of freedom delta d for the ith iteration, and from this you get the strain increment for that particular iteration. And then what we want is we want to calculate the stress. So now the stress is we have is that we will know the what is the stress in the previous iteration. So essentially we can say that we are given stress in the previous iteration at a particular element, particular gas point. So this you are going to do for each element, each gas point, you are going to store these stresses and update them. So for a particular gas point, this is available for the previous iteration, this is given, and then now we want to find the stress in the corresponding to the current iteration. So want to find sigma of I. So how do we do? So I mean if you look at of course this is the corresponding to previous iteration, and this is corresponding to the current iteration. So now how do we do? So one you might actually think that this is a simpler problem, and what you can think of is like writing this delta sigma I for the ith iteration. You can just calculate from the CT we have I minus corresponding to I minus 1th iteration, because it depends on the stress, and stress is available for the previous iteration. So therefore CT is corresponding to I minus 1th iteration into delta of epsilon I. So you may think that we can do this and then update the stress. So sigma I can be written as the straightforward thinking tells us that we can write sigma of I is equal to sigma of I minus 1 plus delta sigma I. So this is what we think that no, we can do it like this. But the problem with this is we are not satisfying in this calculation process. We are not satisfying the yield criteria. So actually this doesn't work. This does not predict the stresses accurately. The reason for that is we do not get correct stresses because yield criteria is not satisfied. So we cannot, that means we cannot use this approach of calculating the stresses. So then how to calculate? That's the next question. Now if we cannot do this, then what do we do? How do we calculate the stress? So now the question is how to calculate, if not this, then how to calculate this delta sigma I. So that's the question. And what I will do is I want to simplify some of the writing over here. So the current iteration I will not write in the subsequent equations I'm going to write. So let me write that. Henceforth, now till I discuss this evaluation of stresses. So henceforth, this delta sigma I will be denoted as simply delta sigma. So now how do we do? So the one idea is that we can now express this delta sigma, that is I can say that express stress increments. These are incremental stresses, so stress increments, express stress increments in terms of incremental equivalent plastic strain. Incremental equivalent plastic strain, and that is basically delta epsilon equivalent P, which we have already defined, and then find delta epsilon equivalent P by satisfying the yield criterion. And this approach is known as return mapping approach. So there is a name for this, is known as return mapping approach. So let me explain you how to do this. So first step is to express the stress increments in terms of the incremental equivalent plastic strain. So how do we do that? So we go back to the basic equation, but we have to some way satisfy the the yield criterion. So we know that delta of sigma, the basic equation we have written in terms of CE. So that is CE into, we have the elastic part of the strain, which is total strain increment minus plastic part of the strain increment. So this we know, and we know that we can write this in terms of CE into del epsilon, and then using flow rule we can write del epsilon P as delta epsilon equivalent P, which is scalar, into del F by del sigma. And now in del F by del sigma, see, del F by del sigma is a function of stress which is unknown for the current iteration. So further what you can do is you can write this as if you substitute, of course we are talking about the the associative flow rule. So delta sigma will be equal to CE, the elastic constitutive matrix, into delta epsilon minus, and you understand which is vector and which is scalar, I think that from the context. So you can say that if we write del F by del sigma in terms of the stresses, so the second term would become delta epsilon equivalent P divided by 2 sigma y, that is yield stress, and then we have this del F by del sigma terms. So twice of sigma xx minus sigma yy minus sigma zz, twice of sigma yy minus sigma zz minus sigma xx, twice of sigma zz minus sigma xx minus sigma yy, 6 tau xy, 6 tau yz, and 6 tau zx. So this is what we have, and now what we want is, first we using this equation we want to express delta sigma components in terms of this delta epsilon equivalent P, and of course the other quantities which are there. So see, what we can do is we can write now in this, the sigma xx, sigma yy, sigma zz are the current stresses for the current iteration, which is unknown. But then what we can say right is, so let us say that sigma xx is equal to sigma xx in the previous iteration, that means I minus one iteration, plus delta sigma xx. Delta sigma xx is an unknown, and similarly all the components. So sigma yy can be written as sigma yy at I minus 1 plus delta sigma yy delta no sigma zz is, all same thing, sigma zz I minus 1 plus a delta sigma zz. You know all the components, you can write like that. Tau xy is equal to tau xy in the previous iteration plus delta tau xy. Tau yz is equal to tau yz in the previous iteration plus delta tau yz, and tau zx will be equal to tau zx at previous iteration plus delta tau zx. So you can write like this, and you will also let us say we consider the isotropic material. So for that we know the expression for C in terms of Young's modulus and Poisson's ratio. I'm going to make use of this, so that is why I'm writing here. So you will see that the constitutive matrix CE is going to be, so let me write over here. So CE will be equal to E upon 1 minus 2 nu for the isotropic material, 1 plus nu, and then we have 1 minus nu 0 0 0, and nu 1 minus nu 0 0 0. So nu 1 minus nu 0 0 0 for isotropic material. For the general 3D case, this is your constitutive matrix, 1 minus 2 nu by 2, so that you can get the shear modulus. So 0 0 0, 1 minus 2 nu by 2 0, and 0 0 0 0, 1 minus 2 nu by 2. So this is the CE matrix you have. Now we can now use substitute. Yeah.
Sir, are we doing this for isotropic hardening, like this evaluation?
No, not really. For the, we are only saying that the the linear elastic behavior is isotropic, but it could be either isotropic hardening or kinematic hardening. So we are not saying about that. It is valid for
replacing del F by del sigma, like we did not consider the
that
alpha.
is for the associative flow rule. Alpha doesn't come. No, see, when you write this relationship, this particular relationship, so this is further it is isotropic hardening or kinematic hardening, it is always elastic constitutive matrix into elastic part of the strain. So that is total strain increment minus the plastic strain increment. So this is valid irrespective of is isotropic hardening or kinematic hardening. The del F by del C alpha doesn't come here when we write this relationship, or when we write del epsilon P. That comes when we write the expression for dF, where F is yield function. So in that you will have,
while calculating del F by del sigma xx, at that time also, like the expression we got for del F del sigma xx was 3 by 2 sigma yyD minus alpha yyD, when it was the case of kinematic
yeah,
hardening.
right. Yeah, so you are saying now here, you are saying
Yes.
at this stage, yeah. So yeah, now yes, you are right that up to here it is valid for either the isotropic hardening or kinematic hardening. But when I write del F by del sigma in this manner, so yeah, then it is for the isotropic hardening. You are right.
Okay.
I think, yeah, if we want to do for a general case, then you also have to include here alpha terms in this, in the no, del F by del sigma xx, del F by del all the terms you need to include the alpha terms. Yeah.
But sir, in
So
above equation also, we are replacing lambda with delta epsilon equivalent. So
yeah, so
how
that is true. That is true for whether it's isotropic hardening or kinematic hardening. That we have, I have given you the proof that
but
no
sir,
alpha.
we are putting the value of sigma xxd sigma yyd in that also while proving lambda equals to d epsilon equivalent p.
No, I didn't get you. Say when you are saying delta sigma, so this relationship is a general relationship.
Yes sir.
This is also a general relationship. Only thing is we are saying that flow rule is associative flow rule, and the equivalent incremental plastic strain and lambda we have already shown that the two are equal. That proof I had shown.
Sir, while proving that proof, we replaced sigma xxd value, sigma yyd value.
You are saying that we did not include the alpha terms in that.
Sir, as in below equation, we
Yeah. So
sigma and
that's
sigma.
what. So that's what I'm saying here. When I'm writing, this expression is for isotropic hardening. When we write del f by del sigma xx del sigma yy, all these terms, so this is for isotropic hardening. If we have kinematic hardening, so we'll have to also include the alpha terms in these, in del f by
So,
del
sir,
sigma.
while proving lambda equals to d epsilon equivalent p, we have
Yeah,
used sigma xxd, sigma yyd values. That means these values. So these values are for
isotropic hardening.
hardening. So while proving that, we have also used these values. So that should also be for isotropic hardening.
Yeah, so when
Lambda
you are,
equals to delta.
so that we have started with the definition of equivalent strain, and then we have written these plastic strain in terms of del f by, of course, del sigma, and del f by del sigma terms we have substituted. Yeah, but that comes true for the kinematic hardening also. But yeah, the derivation we did is, yes, we have shown it for the isotropic hardening. Yeah, you are right. There also we had del f by del sigma xx and so on, and that we just wrote in this form. So this equation is general. Yeah, this equation is general, but it turns out that for the kinematic hardening also, the plastic strain, equivalent incremental plastic strain, is equal to lambda, but we have not proved that. Yeah, it can be proved in that. You will get the same form. So but directly, yeah, it appears that this is for the isotropic hardening, but it if one takes that also, you will get the same relationship. Lambda is equal to delta epsilon equivalent p.
So irrespective of hardening and associative flow rule, irrespective of hardening plus associative flow rule, we got the second equation.
Lambda is equal to delta epsilon equivalent p. Yeah.
Okay, sir. Thank you.
Yeah. Okay. So yeah, so I just want to demonstrate this. So how to, I mean, the same thing you can do for the kinematic hardening by including the alpha term. Only thing is the expressions would be more involved. So now if you see, once we look at this, so now we make use of these relations, what I have just written over here, these ones. So now if we substitute this expressions over here, now in this equation, so then what you can do is you can write this delta of sigma is equal to Ce, elastic constitutive matrix, into delta of epsilon and minus delta of epsilon equivalent p upon 2 sigma y. No, you can do a similar derivation for kinematic hardening. Yeah. So now here you will have this. Now the stress, total stress is written in terms of stress in the previous iteration and the increments. So this whole thing can be written as twice of sigma xx I minus 1 minus sigma yy I minus 1 minus sigma zz I minus 1, and similarly you can write plus twice of delta sigma xx minus delta sigma yy minus delta sigma zz, and like that, no, you can write all the terms, in the similar manner. So this is what you can do, write it like this. So now finally you would be able to do one thing. Now we have this first term, Ce into delta epsilon. So C is the elastic matrix, delta epsilon is the total strain increment in the ith iteration. So if we take this as some multiplication as some vector s, the tensor s, so you can say that is kind of, we can say that the predictor. So the predictor we are taking as the assuming that this step is elastic step. So that means you can write this equation as delta sigma is equal to the first term we are writing s. So this product I am saying as basically tensor s, which is the elastic predictor stress, and then minus you have delta epsilon equivalent P into constitutive matrix CE divided by 2 sigma y, and then you have these terms the way I just wrote. So you will have basically all these terms will be coming over here. All the set of terms you get it there. Here I have already said where this S is C into delta epsilon, so it is elastic predictor. So we are assuming that the stress is elastic, so this B is also referred to as elastic predictor. So then now if you let me take one component at a time. So now if I take from this delta sigma xx, so you can see that delta sigma xx can be written as sxx minus delta epsilon equivalent P divided by 2 sigma y, and then but now we are taking the multiplication of this CE here, CE and the rest of the terms, the terms which you have here. So that you can check, you will find that this will come out as, of course, E upon 1 minus 2 nu into 1 plus nu, and then we will have in the bracket here we will have 1 minus nu into we will have the the previous step stress terms, and we will have the incremental stress terms. So let me write all of them and you can cross check. So this will be twice of sigma xx at I minus 1 minus sigma yy at I minus 1 minus sigma zz at I minus 1. Then similarly we'll have plus nu times twice of sigma yy at I minus 1 minus sigma zz at I minus 1 minus sigma xx at I minus 1. Then plus nu times you are going to have twice of sigma zz at I minus 1 minus sigma xx at I minus 1 minus sigma yy at I minus 1. And then you will also have plus here, you will continue in this whole the bracket term. So you will have 1 minus nu into the incremental terms. So twice of delta sigma xx minus delta sigma yy minus delta sigma zz plus nu into twice of delta sigma yy minus delta sigma zz minus delta sigma xx plus nu into twice of delta sigma zz minus delta sigma xx minus delta sigma yy. So this is what you will get, and you can simplify this. So you would be able to write this as you can do the simplification. So now collect the terms. So what you will be able to do is you would be able to write this as delta sigma xx is equal to sxx minus delta epsilon equivalent P divided by twice of sigma y, and then of course we have E upon 1 minus 2 nu into 1 plus nu, and then you would be able to write here no, you can club all the terms together. So you would see that you can write this as 1 minus 2 nu into twice of sigma xx at I minus 1 minus sigma yy at I minus 1 minus I think it is not writing, so let me open and close. There's some problem. So is the screen visible? Hello?
Yes, sir.
It is visible.
Yeah, so the derivation is bit lengthy. So yeah, you have to bear with me. So this is minus sigma zz at I minus 1. Now again, I think there is a problem. Yeah, so I think there was again in between there was a problem. So I think now is the screen visible again?
Yes, sir, it is visible.
Okay. So this is sigma zz I minus 1. So that is one term you will get. And similarly plus 1 minus 2 nu you will get. Now if you club all the terms you will be able to get it like twice of delta sigma xx minus delta sigma yy minus delta sigma zz. So you can write it like this. Now 1 minus 2 nu from here and here can be cancelled out. So finally and then you will have yeah, you can write yeah, basically e upon 2 into 1 plus nu as g. So finally you would be able to let me write as it is. So you will be able to write this expression as delta sigma xx is equal to sxx minus you can say delta epsilon equivalent p upon twice of sigma y into e upon 1 plus nu, and then inside here what you will have is uh, twice of sigma xx at I minus 1 minus sigma yy at I minus 1 minus sigma zz at I minus 1, plus we will have twice of delta sigma xx minus delta sigma yy minus delta sigma zz. So this is what now you can write. So now similarly you can write the other components. So similarly now if you look at the delta sigma yy and delta sigma zz, they can also be written in a similar manner. So delta sigma yy would be syy minus delta epsilon equivalent delta epsilon equivalent p upon 2 sigma y into e upon 1 plus nu. So I think you can, it would be in the same form, twice of sigma yy at I minus 1 minus sigma zz at I minus 1 minus sigma xx at I minus 1 plus twice of delta sigma yy minus delta sigma zz minus delta sig. So it is coming out to be, you know, in a simpler form, the expressions for these incremental stress. And similarly you can write delta sigma zz would be szz minus delta epsilon equivalent p upon 2 into sigma y into e upon 1 plus nu, and then twice of sigma zz at I minus 1 minus sigma xx at I minus 1 minus sigma yy at I minus 1 plus twice of delta sigma zz minus delta sigma xx minus delta sigma yy. So you can write it like this. So now what you I want the expression for delta sigma xx, delta sigma yy and delta sigma zz in terms of basically the equivalent plastic strain. So what you can do now, if you sum these three equations, this equation plus this equation plus this equation, so you will find that the second terms which are coming with their delta epsilon equivalent p, they will get cancelled out. So from these three equations you can say that delta sigma xx plus delta sigma yy plus delta sigma zz, this will be simply equal to sxx plus syy plus szz. And let me denote this by simply saying that it is sigma s. So now what we can do is actually now the first equation, if we look at this equation, so here what we can do is right now if I want it is in terms of all the three, delta sigma xx, delta sigma yy, delta sigma zz. But now if we right here I subtract and add delta sigma xx, so we will have 3 times delta sigma xx minus delta sigma xx minus delta sigma yy minus delta sigma zz. In place of minus delta sigma xx minus delta sigma yy minus delta sigma zz, we can write this minus sigma s, and then we can solve that equation for delta sigma xx. So that is what will give you. So now if you take this equation, so from this equation you will be able to get the final expression for delta sigma xx, you can write it as delta sigma xx, making use of this relationship, is equal to sxx minus delta epsilon equivalent p upon sigma y, and e upon 2 into 1 plus nu, I am writing g, shear modulus. So this is g, and then here of course the initial stress terms would be there. So twice of sigma xx at I minus y minus sigma yy at I minus 1 minus sigma zz at I minus 1. This will be there, and then we will have plus 3 times delta sigma xx and minus this summation s. So this is what we will have, and now we can solve this for the delta sigma xx. So you take this delta sigma xx term to the left hand side and then solve for delta sigma xx. So you will finally will be able to say, no, you will be able to get this, that delta sigma xx is sxx minus delta epsilon equivalent p upon into g upon sigma y, and into we will have this twice of sigma xx at I minus 1 minus sigma yy at I minus 1 minus sigma zz at I minus 1 minus this sigma s. So this is inside the bracket, and this whole thing is divided by 1 plus 3 times delta epsilon equivalent p into g upon sigma y. So now see, what we have done is we have written this delta sigma xx in terms of delta epsilon equivalent p. This is known because that is simply c into delta epsilon, so that is known. G is a material constant, shear modulus, so that is known. So and these are the stresses in the previous iteration, so that is also known. That the sigma summation s is also known. So only unknown is this delta epsilon equivalent p. So this, and of course sigma y for the isotropic hardening will also be function of delta epsilon equivalent p. So ultimately everything is in terms of delta epsilon equivalent p on the right hand side. So through this we are able to express the stresses in terms of stress increments in terms of delta epsilon equivalent p. So that is what we are able to do. So similarly, the way I have shown you, yeah.
Sir, how this last equation is coming on denominator?
So now see, if you look at here, this side, this delta sigma xx is there, and then if you look at this term, so there is a minus sign here, and this will be this whole term will be multiplied with this 3. So you will get 3 delta epsilon equivalent p g upon sigma y into delta sigma xx, that you take to the left hand side, and then delta sigma xx, the whole thing you divide by that.
Okay, sir.
So you are just solving for delta sigma xx from this equation.
Okay, understood, sir. Thank
Yeah, okay. So then you have this delta sigma yy. So this similarly, I'm just writing the final expression. So this would be syy minus delta epsilon equivalent p into g upon sigma y, and into twice of sigma yy at I minus 1 minus sigma zz at I minus 1 minus sigma xx at I minus 1, and minus sigma s, and this whole thing is divided by same, then denominator is same, 3 times delta epsilon equivalent p into g upon sigma y. So now similarly you can write delta sigma zz is equal to szz minus delta epsilon equivalent p into g upon sigma y into twice of sigma zz at I minus 1 minus sigma xx at I minus 1 minus sigma yy at I minus 1 minus sigma s, and this whole thing divided by 1 plus 3 delta epsilon equivalent p into g upon sigma y. So this is what you get for the normal increments in the normal stresses, delta sigma xx, delta sigma yy, and delta sigma zz. So yeah, then same thing you have to do for the shear stresses. So if you take the fourth equation, you will be able to write so let me say also delta tau xy, if you look at, is equal to sxy. We are again taking this equation, the equation what we have over here, this equation. So from this equation I am taking the fourth one, that is delta tau xy. So you will see that delta tau xy will be equal to sxy minus delta epsilon equivalent p upon twice of sigma y into E upon 1 minus 2 nu into 1 plus nu, and inside this we will have, let me not put the curly bracket, inside this we will have 1 minus 2 nu by 2 into 6 times tau xy at I minus 1 plus 1 minus 2 nu by 2 into 6 times delta tau xy. So you will have this term, and so you can solve this similarly the way I just said. So from this you will be able to say that delta tau xy will be equal to sxy minus 3 times delta epsilon equivalent p into g upon sigma y into tau xy at I minus 1, and the whole thing is divided by 1 plus 3 times delta epsilon equivalent p into g upon sigma y. So same way now you can write tau delta tau yz and delta tau zx. So yeah, now say, so same way now you can write delta tau yz. I think, you know, if you do yourself you will be able to get that it is, you know, straightforward steps, although little bit lengthy, but straightforward. So syz minus 3 times delta epsilon equivalent p into g upon sigma y into tau of yz at I minus 1th iteration, and whole is divided by 1 plus 3 delta epsilon equivalent p into g upon sigma y. So also you will be able to write tau z, delta tau zx is equal to szx minus 3 delta epsilon equivalent p into g upon sigma y into tau zx at I minus 1th iteration, and whole is divided by 1 plus 3 delta epsilon equivalent p into g upon sigma y. So once you have this, so now what we are able to do through this, we are able to express the stress increments delta sigma xx, delta sigma yy, delta, all the stress increments in terms of this one parameter epsilon equivalent p. So we have a single unknown parameter now to evaluate these stresses. And how do we find this? This we find by satisfying the yield function. So now find delta epsilon equivalent p. And how do we find that? We find that by satisfying the yield function. So we say that f, which is a function of say sigma and plastic work. So for the timing, yeah, let me say for the isotropic hardening, so sigma wp is equal to 0. For the now I'm talking specializing to isotropic hardening, and let the initial guess, because now again this is a nonlinear equation, so again you have to use Newton-Raphson method. So we need an initial guess. So let the initial guess for delta epsilon equivalent p be 0. So you actually can take it as 0, the initial guess, and then use the Taylor series. So now this equation we can write as a, you know, f function f evaluated at delta epsilon equivalent p corresponding to, let us say, the previous k minus 1th iteration, and plus then you will have del f by del sigma transpose and into del sigma by del epsilon equivalent p, and this whole thing is evaluated at delta epsilon equivalent p corresponding to k minus 1th iteration, into you will have the this term, of course, yeah, there would be one more term, so let me write all the terms together. We are just using the Taylor series to solve this ultimately, because all the stresses are in terms of delta epsilon equivalent p, so we are able to solve this equation for delta epsilon equivalent p. So yeah, this is, yeah, there's one more no correction over here. So this is delta of delta epsilon equivalent P, and plus we will have del F by del WP, and then del WP by del of delta epsilon equivalent P, and this whole thing is evaluated at delta epsilon equivalent P in the k minus 1th iteration, and then here into, so we will have into delta of epsilon equivalent P for the kth iteration is equal to 0. So from this equation you will be able to solve for this delta of delta epsilon equivalent P. So solve for delta of delta epsilon equivalent P k for the kth iteration, and then update, then write delta epsilon equivalent P for the kth iteration is equal to delta epsilon equivalent this P for k minus 1th iteration plus delta of delta epsilon equivalent P for the kth iteration. So from here you will be able to find out the delta epsilon equivalent P, and once you get delta epsilon equivalent P, and then you go back to these expressions and calculate the stress increments, and once you have the stress increments you can calculate the total stresses. So the let me say that the overall, yeah, the over let me, yeah, so I'm taking little bit more time. So then finally what you will say, if you look at the overall solution, briefly I'm telling about briefly, overall solution procedure is going to be, first you solve this kt I minus 1 into delta di is equal to f I minus 1. From this you get your delta di, and from then you get the delta d, get delta epsilon, so you get delta epsilon I from this, and then you calculate, we have already got the equation how to find this delta epsilon equivalent P for the finally after carrying out the iterations over this k, we will get delta epsilon equivalent P for the ith iteration, and then from this you will be able to get finally the stress increment for the ith iteration, and therefore finally the sigma for the ith iteration, and then you go for the next iteration till the solution converges. So now how we'll write, so of course if you look at the sigma total stress, you will write at each gas point sigma I is equal to sigma in the previous iteration plus delta sigma I calculated over here, and so similarly we'll calculate delta epsilon equivalent plastic strain also you need to calculate, so that would be delta epsilon equivalent for the I minus 1th iteration plus delta epsilon equivalent P for the ith iteration, and then you also need WP. So WP you will be able to calculate WP for the previous iteration plus sigma yi for the current iteration into delta epsilon equivalent for the ith iteration, and so this is how we will solve the problem. That's the total solution procedure. So now let me just uh, let you know that how we how the solution is progressing in the stress strain curve. So if we, for the multi-axial case, if we take the sigma equivalent, which is similar to sigma xx for the uniaxial load, and epsilon equivalent here, and then we basically have the stress strain curve. So sigma equivalent versus epsilon equivalent is similar to uniaxial stress strain curve. So you have this, and then you have this part. So the whole load you are going to divide into a number of steps. So of course these steps would be elastic steps. So you go from 0 to this step, this to this step, this to this step, till this you are in the elastic region, and then you go into the elastoplastic region. So once you go to the elastoplastic region, the iterations start. So all those iterations what I have talked about, you have to uh, uh, solve that. So this is how the overall solution procedure. So like you have a number of steps, and each iteration, in each step there are iterations, and actually there are global iterations. So one is to get the converged delta d, so that is a global iteration, and there is a local iteration to calculate this delta epsilon equivalent. So there is another iteration over here, no, as you see from this equation. So there is a global iteration, there is a local iteration. Global iteration to get the converse delta d, that is the iteration variable I have set as I, and then the local iteration which is at each gas point of the each element, so that is the iteration variable I have used k. So there are two set of iterations, global and local iterations, which are involved here. So this is how you will solve the problem. We will actually continue. I will also let you know the some more ways to update the stresses. This is of course more involved, and if you want to extend it for the kinematic hardening, so then you have to everywhere include the alpha terms in the del F by del sigma, and then you can continue. And similarly, of course, when you're doing that, so you will have here also, when you write this, it would be function of sigma and alpha. So that is how you will have to change this. So I think this is where I want to stop, and now if you have any questions and doubts that you can ask, and yeah, so let me, before I take the questions, so let few things about the minor. So the minor is going to be on Sunday, and that is 19th of September, and the timing would be 9 to 10:30 for solution, and then from 10:30 to 10:50 for uploading the solution in grade scope. So you are going, the question paper will be there in grade scope, and you will have to upload the solution also in the grade scope. And so when you upload your PDF in the grade scope, after uploading the PDF, do select there would be number of questions. So for each question you have to select the pages. So do that, so that it is clear that which pages are for which question and all. And when you are writing, we start each question on a first page, so that you are easily, very easily able to select the pages for a particular question. So you should do that. Additionally, I will, I have not yet created the same thing in Microsoft Teams, but I would ask you to also log in Microsoft Teams and keep your camera on, so that I'm able to see what you are doing. So I will also be monitoring how you are doing, so that there are no unfair means and all. So you have to also log in the Microsoft Teams in the course ML805, and switch on your camera, and I will be watching that each and every one of you, that you are doing your own work, not doing any unfair means. Yeah, so now you can ask questions and doubts. Hello?
Sir, will this test be like open book?
Yeah, this will be just open book, open notes.
Okay, so we can use our class notes, right?
Yeah, you can use your class notes, yes.
Okay. And sir, actually about the book, like I have like printed a part of it, so can I use that printed copy
You
also?
can use, yes, it is open notes, open book, so you can use your notes and your books also.
Okay, sir.
Yeah. Any other doubt, question?
And sir, can we use the PDF of
Today's part
book?
will also be in the syllabus, or is it?
Yeah, I think whatever I have covered till today is part of the syllabus. Of course, I will see what questions to give, but yeah, the entire thing is part of minor syllabus.
Okay.
Yeah.
And sir, can we use the PDF mode in laptop while exam is going on? PDF mode of book.
Yeah, you can use that. There is no problem. You can use that.
Okay, sir.
Just hello. हाँ जी सर. I'm just finishing sir my class, so मैं आपको 5 मिनट में कॉल करूँ. हाँ ठीक. Yeah, yes please.
So team link will be provided, or we'll just log into the team?
Yeah, I will say, no, I will say, yeah, I think I will give you link. Yeah, that is better.
Sir, actually there is one Teams group for this course also.
No, but I think maybe I will generate the link from there itself. So I will send you a link. So in AML805 the rate of courses.itd.ac.in, I think I will send in that, so all of you will get that link.
Syllabus will be up to this lecture.
Hello, sir.
Yeah, syllabus would be up to today's lecture.
Sir, I have a question.
Yeah.
Sir, actually, I'm a part-time student, so I'm not in touch with anyone in this subject. So, can you tell me the procedure for forming the group for the assignments? Is there any WhatsApp group where I can get in touch with someone
I think you
for
can.
this?
No,
Hello.
I think
Hello. There is a
Sir,
WhatsApp group. You can join, okay?
who is this? Can I get in touch with you?
Yes, Anup Pathak.
Okay, okay. I'll text you on Teams then.
Okay, no problem.
Okay. Thank you, sir.
yeah. Okay. So, are there any other questions? Yeah. So, if there are no questions, I am stopping. Thank you all for your attention.
Thank you, sir.
Okay.